We are almost done with our second order homogeneous differential equation using constant coefficients. Not quite done because there's one case that we have not yet considered. As we do our normal task of substituting in the form of the fundamental solution and thus getting this characteristic equation, we will, as usual, solve this as a quadratic equation and come up with the solution that we're very familiar with. This time we're assuming b squared minus 4ac is equal to 0. That neutralizes the effect of the plus and minus, leaving us only one solution, and that is minus b over 2a. Now that's a problem. First you think that's going to make things simpler because you just have one solution to deal with, but that's not the case. We spent a lot of time in section 3.2 proving that these problems will be guaranteed to have two fundamental solutions. So rather than making things simpler, all we did is make our tool less powerful because prior to this, it gave us both solutions. Now it's only yielding up one, and we're going to have to find another way to get at the second one. So here's our first fundamental solution. We're going to make use of it, of course, and we'll end up having that be a first solution in a linear combination with some y2 that we have yet to identify. Okay, so we know y1 is a solution. We know that any constant times y1 would also be a solution. But we are going to use this y1 as a means of kind of leapfrogging into y2. And we'll assume, and this is an assumption that needs some verification, that we can take some unknown function v, multiply it by y1, and the product will be y2. Now, I don't know what the function of v is. It's a function of t, but I don't know what the form of it is. Maybe it's the sine of t, maybe it's e to the t, maybe it's a hyperbolic cosine, maybe it's a tangent, who knows what it is. But we will assume that it's possible to do that. That's an assumption. I didn't prove that. We're going in by faith on that one to see if it's there. So we've got a lot of historical momentum to help us out, but we'll go ahead and use that. So here's our y1, and we're going to attempt a y2 to be in this particular form. Well, if that is a solution, then I should be able to plug y2 and y2 prime and y2 double prime back into the original differential equation and have it be equal to 0. So let's give it a try. Well, that means we've got to do a bit of differentiation. So here's our y2, that's our assumed y2, and y2 prime will require the product rule. So what does that say? Well, it says I differentiate one function and multiply that by the second, and then add that to the first function times the derivative of the second. That's what we have here. I'll let you verify that later, that that differentiation was done correctly. But we also need the second derivative, and that's going to get a little bit messy because I have a product rule here, and I have yet another product rule over here, and that is going to end up yielding 4 terms by the time I do all this differentiation. Again, you can check that later to verify it's done correctly. One slightly simplification benefit we're getting is the two middle terms are the same. So we can at least combine those together and make it a minus 2 times just one of them. Okay, now you're not going to like the next page, but here it comes. So we'll do it in sections. Reminding ourselves that this is the problem we're trying to solve, we now have to go back and put y2 in here, y2 prime in here, where my cursor's moving around, and y2 double prime has got to go there. So this is a little warning. It's going to get to be a little bit messy. So let's go ahead and do that. And this first line is accomplished by doing just exactly what I said. So this term in brackets here is y2 double prime. You can check that on the previous page. I'm not going back there to do it, but you can check it if you want. All of that y2 double prime times a is this term here. When we take y2 prime, that's in this bracketed term. You can go back and check that also. And that's multiplied by b. We got that from the middle expression. And the last expression is c times y. Well, y was pretty easy. That was just our function of t times times the y2. Now comes the algebra. Well, we'll start combining terms together and see where we can go with that. First of all, we can divide this whole equation by e to the minus bt over 2a and get rid of that because when we divide, or 0 divided by that is 0 anyway. So now if we multiply through the a, we're going to get a v double prime. We're going to be able to cancel this a with this one, leaving us just a bv prime. That helps a little bit. And this a can cancel with one of those two a's, the a squared there, and we end up getting this coefficient times v of t. So that takes care of that part of it. Now we'll start distributing through the b constant. So we have a bv prime, that's right here. We multiply through b again, we'll get a b squared over 2a, so that you'll see here, times v of t. And finally we get our last term tagging along cv of t. Well, that actually looks a little better. That's not too bad. Well, let's do some more combining of terms and combine the second derivative term together. There's only one of those, nothing to combine. Let's look for all the v primes. Well, here's a v prime. It's minus b times v prime. And if we keep looking around, we find a plus b times v prime. And I don't see any other v primes in there. So that's nice. So those two will cancel. The minus v prime plus the v prime goes away, so there is no first derivative. That's kind of interesting. And finally, we'll combine all of the terms associated with v itself. And we see one here, a b squared over 4a, another b squared over 2a. That looks like we'll be able to combine those pretty well. And we have a c. So let's put those together, all multiplied by v. So we can do a little bit more simplification by putting these three terms in a common denominator. Put those all together and we get a little bit more cancellation here because we get combining actually, because b squared over 4a minus 2b squared over 4a is just minus b squared over 4a, and this other term will tag along. So this all now can be put under a common denominator, and we have this expression, which is now getting simpler than before, and it looks a whole lot like the pendulum problem, kind of, when you think about it. So now I'm going to make the audacious statement that this entire expression simplifies to simply v double prime equals 0. Can you see that? That doesn't make sense, does it? Look. We can take this big complicated expression that's got a v double prime, a bunch of terms, times a v, and claim that this equation is exactly the same as just saying v double prime equals 0. Think about that for a minute. That's kind of surprising. Well, if you look closely, you'll see why. We are assuming in this section that b squared minus 4ac is equal to 0. That means this whole term is 0, and therefore there is no v term at all. I end up with just a times v double prime equals 0. A is a constant. We are definitely assuming a is not 0, otherwise we wouldn't have a second order differential equation to begin with, so that would be kind of silly to even be thinking about this if a were 0, and therefore v double prime must be 0. Wow, we took this big old mess up here and said that was equivalent to the second derivative of v being 0. That means if you integrate this twice, you get a linear function of t, and this v of t now will work when multiplied by y1 to produce a new solution. Now that's pretty amazing that would even work at all. You might want to stare at that a bit to convince yourself that's true, but it really falls down and plays dead. So let's go to the next slide and see what we can do with it. Our general solution, therefore, must be a linear combination of y1, there's y1, and y2, which is our v of t times y1. But our v of t was the simple linear function, and so if I distribute this through, and I combine the two terms together that don't have a t multiplied by it, in other words, I combine k1 and k4 into a single constant, then I can rewrite that as these two other constants times these very simple functional forms. Look at that. y1 is what we got when we solved the quadratic equation. y2 is y1 just multiplied by t. I don't even need an extra constant term because it lines up with y1. So we have a very simple way, even though it looked like it was going to be a disaster, we have a very simple way of finding both y1 and y2. And that then becomes the solution for repeated roots. This method only works if b squared minus 4ac is equal to 0. Don't try this on anything else. Why? Because we assumed in the derivation that b squared minus 4ac was 0. Remember, we got rid of a big ugly term with that assumption. So if it's not true, then there's no way that this can work because that assumption is going to be wrong. So this only is to be applied for this special case of b squared minus 4ac equals 0. Pretty nice. Okay, now let's make our next check to make sure this thing should be a solution, because from section 3.2 we found that if you can show the Wronskian is equal to something other than 0, then this is a bona fide solution to the problem. So here's our y1, here's our y2. Let's go ahead and compute our Wronskian. We'll do it the traditional way by setting up the determinant. So here is our y1 again and y2 in the first row of our 2x2. Differentiate each one of them and put them in line 2. Do the cross multiplication and subtract out the off-diagonal multiplication. And you get what looks like a fairly complicated expression, but it's not that bad. It just boils down to e to the minus bt over a. And you know that can't be 0 because an exponential never is 0 for any finite value of t. So y1 and y2 are now proven to work. We guessed that it might be a solution. We got kind of lucky, actually. I'm sure that the guys that originally developed this tried lots of things and they came up with that. And if you can show it works, it works. It doesn't matter how you arrived at it as long as it works. So pretty nifty solution. Let's try a couple examples to get used to it. Here's our second order differential equation. We're going to solve that using the, well, we could solve that using the quadratic formula, but in this case, it's pretty easy. This is going to turn into r squared plus 4r plus 4 equals 0, and this evenly factors into the square of r plus 2. Clearly, you're only getting one root out of this. Same thing would have happened if you'd used the quadratic formula. Well, that's fine. So we take our y1, and we now know we can form y2 by taking some function v times y1. Now, for some reason, your book went through and did all this work the hard way. What you could have done is just put t in here because we proved in general that that works. So let's skip all that and just admit that v of t equals t, and our y2 is t e to the minus 2. So that gives us a general solution, which is a linear combination of those two fundamental solutions. So let's go ahead and plug in our initial conditions. We're going to assume that the initial value of y is 1 and its velocity, so to speak, is 3. And we'll end up with these two equations. How do we get that? Well, we plugged 0 into both of these, and the 0 is going to get rid of this portion of the solution completely. So all we get on the right side when t equals 0 is c1. And we are forcing that equal to 1, which is how we get c1 equals 1. If we differentiate this, we'll get a minus 2c1 e to the minus 2t. And this is going to require the product rule again, because you're going to have to differentiate t and multiply by e to the minus 2t, and then take t times the derivative of e to the minus 2t. If you do all that math, which isn't too much, you'll end up getting minus 2c1 plus c2 is equal to 3. Easy to solve that. So we know that c1 is equal to 1. And we can just plug in a 1 here. Substitution would be the easiest way to go. We now know that C1 and C2 is 1 and 5, and so we end up with this expression. You can plot it. Looks kind of cute. There it is. And you're done with this example.